Right, ladies and gentlemen, let's continue with chapter 11 on heat exchangers. With the previous lecture, we looked at the different types of heat exchangers, the most important types. It's not all the types, but it's typical types that you're going to get in this chapter. And then we've addressed the issue of the overall heat transfer coefficient, and then also in terms of fins. Let's just go back to the overall heat transfer coefficient, because we are going to continue with that today and we're going to use it. So it says 1 divided by the overall heat transfer coefficient multiplied by the surface area. We can write it as the overall heat transfer coefficient based on the area on the inside of heat transfer, or we can base it on the area on the outside heat transfer area. And 1 divided by UA is equal to the thermal resistance. The thermal resistance in which you've done in chapter 3 in the previous module, and you can write that resistance terms as 1 divided by the heat transfer coefficient multiplied by the surface area plus the resistance of the wall, plus 1 divided by the overall heat transfer coefficient multiplied by the surface area. This is this modeling that you did previously in chapter 3. There's a temperature difference T1 and T2. There will be a heat transfer rate in that direction. And this will be the resistance 1 divided by the heat transfer coefficient on the inside. So the convective stream on the inside, the resistance of the wall. The resistance of the wall can be written in terms of different formats. If it's a plain wall, then it is equal to something like K divided or T divided by Ka, where T is the thickness. Otherwise, where it is a cylindrical type of geometry, it's the ln of the diameter ratios divided by 2 pi KL, and this resistance term is equal to 1 divided by the heat transfer coefficient and the surface area. And this overall heat transfer coefficient can then be written as the resistance delta T divided by the resistance, something like that. Okay, do you remember that? Okay, so with the previous lecture we've addressed that. Then we've looked at this total surface area. In many cases, if you've got a heat transfer stream, let's suppose you've got a fluid here on the inside, and it can be a single phase fluid, or it can be a fluid that is boiling or condensing, and you would like to transfer heat to the environment. Then you can make use of this surface. So that will be the surface of heat transfer. Normally, you will see that the air requires a lot of surface. You're going to use many square meters. And one way of improving the heat transfer is to make use of fins. I'm going to show it like that. And then we're going to say, well, this total surface area is going to be the total area of heat transfer, and that would consist of the area of the fins plus the area of the unfinned area, the unfinned part. Okay, now the unfinned part would then be these areas there. So that would be the unfinned parts, and the finned parts would of course be those areas there of the fins. That part there. Okay, so it's very easy to calculate. However, there is something else that we need to remember, and that is that normally the fin efficiency plays a big role. So we can write the surface area as the area unfinned plus the efficiency of your fin multiplied by the area of the fin. Now the question is, where do we get this efficiency of the fin? Well, you have to go back to chapter 3, and if you go and look in table 3.3, all the results are summarized in your textbook. So I'm going to show it to you quickly, for in case you forgot about it. There they are. Okay, just the top part. There you can see the case for the rectangular fin, and the fin efficiency is the hyperbolic MLC divided by MLC, and therefore all the different types of fins, you can get the fin efficiency in terms of the geometry which is being used. Something else that we have to take into consideration when we look at heat exchangers is fouling. And we do that by an extra resistance term, RF. And I would like to show you some photographs of typical fouling that can happen on a heat exchanger area. So there's, for example, some scale. You can all see it in many of the kettles that you use to boil water, especially in very specific parts of the country. That scale can build up to quite a few millimeters, sometimes 10, 20 millimeters. And then also in the hot water storage tanks, the geysers, they can really build up there. This is typically what can happen in a shell and tube heat exchanger. There, in many cases, it's not only scaling, but it can also be corrosion. Look there. These are, of course, extreme cases. Normally, it is not that bad. There you can also see how the tubes would start blocking of it. And in general, in table 11.2, there are some values of RF, this fouling factor, this extra resistance. And you'll see that these values are approximately in the order of 10 to the minus 4, and the units are square meter Kelvin per watt. Now these are just values, but in many cases they are very difficult to understand. But if you can take this and you can do some calculations, you can actually show that 0.2 millimeters of limestone, that typical scaling thickness of 0.2 millimeters would give you the same effect as limestone with a K value of 2.9 watts per meter Kelvin. And how do we take this fouling factor into consideration? Well, in heat exchangers, there's more than one area. So typically, let's look at a double pipe heat exchanger. There is the one tube there, and there is the other tube on the outside. Okay. Now again, it doesn't matter on which side is the hot part, the hot fluid, and or the cold part. Previously I've drawn it there, so today I'm just going to put it through there, through the annulus, and the cold water through there. Okay. So, and in most heat exchangers will be insulated. You don't want heat transfer to the environment, so there's your insulation material. So there's your insulation. So it's very important to notice that the scaling or the thermal resistances because of fouling will almost never occur on these surfaces because it's an adiabatic surface. There's no heat transfer. The heat transfer will occur through this surface from the hot side to the cold side in this case. So the heat transfer will be there, and what we're now going to do is the fouling that's going to that's going to occur there, we can refer to that as the fouling on the outside. Okay. And then there will be fouling there, which is called the fouling on the inside, RFI. Does that make sense? And the total resistance then, we're going to write the total resistance as equal to 1 divided by the heat transfer coefficient on the inside multiplied by the area on the inside plus the fouling resistance on the inside multiplied by the area on the inside plus the resistance of the wall plus the resistance of the fouling on the outside, the area on the outside, plus 1 divided by the convective resistance on the outside, over the outside surface. So you will see that the two resistance terms is just added like that. Now in industry it is not so easy to know what that value is going to be. Of course, if you've got a heat exchanger in operation, you can go and measure it after 10 years or so. But the problem is, let's suppose it is water, then that doesn't mean that for the next year you're going to get the same thing, because water quality can actually varies quite a lot from day to day. So it is a very difficult thing to beforehand determine and or estimate what it will be. You do get these foulings, resistances, not only into systems where there's liquids, but you also get it on fins. So if some of you can go and look at, obviously I'm drawing these fins far apart from each other just to make it clear, but normally these fin distances is 1 to 2 millimeters. So you can go and look at many condensers and or evaporators on the sides of buildings. After a few years, you will see lots of dirt and leaves and many things that can actually also cause this additional fouling. Also with fossil fuel power stations, especially the dry cooling type, where they've got big fans that increases the heat transfer that takes the air and would blow it over all these fins. Something like moths, everything, they end up into between these areas, and they can really clog it up very, very badly. Okay, so let's look at an example. And this example is a tube-in-tube heat exchanger. Double pipe heat exchanger, and it looks like this schematically. And there's going to be in the annulus oil that would enters there at a mass flow rate of 0.8 kilograms per second. Then through the inner tube, we're going to have water with a mass flow rate of 0.5 kilograms per second. Now, something that they're going to make easy for us is they say that the average hot water temperature is 80 degrees Celsius, while the average oil temperature is 80 degrees Celsius, while the average water temperature is going to be 45 degrees Celsius. It's very unusual that the values would be given like that. Normally it would be the inlet and or outlet temperatures that will be given. What they also give us is that this diameter on the inside, the diameter on the inside of that tube is 30 millimeters. This diameter there is 30 millimeters. And this wall is given as a very thin wall. And we are asked to determine the overall heat transfer coefficient. I beg your pardon?
You wrote the both diameters.
Ah, okay, sorry, I'm, as you know, crazy. Okay. Yeah, sorry, that is 20 millimeters, and that one is 30 millimeters. So now we've got two fluids. Let's summarize it here. So we've got the oil at 80 degrees Celsius, and we have the water, which is the average temperature of 45 degrees Celsius. And we need to go and get the properties. The properties you can get in your textbook. The oil properties, the density, it's equal to 852 kilograms per cubic meter. The Prandtl number is equal to 499.3. The thermal conductivity K is equal to 0.138 watts per meter Kelvin. And the kinematic viscosity is equal to 3.794 multiplied by 10 to the minus 5 square meters per second. And on this side, the density of the water is 990.1 kilograms per cubic meter. The Prandtl number is equal to 3.91. The thermal conductivity K is equal to 0.637 watts per meter Kelvin. And the kinematic viscosity is equal to 0.602 multiplied by 10 to the minus 6 square meters per second. Let me repeat the values. Oil, 852 kilograms per cubic meters. Prandtl number, 499.3. Thermal conductivity, 0.138 watts per meter Kelvin. The kinematic viscosity, 3.794 multiplied by 10 to the minus 5. The density, 990 kilograms per cubic meters. Prandtl number, 3.91. Thermal conductivity, 0.637. And kinematic viscosity, 0.602 multiplied by 10 to the minus 6 square meters per second. You've got everything? Okay. What is the question again? The question is we have to determine the overall heat transfer coefficient, and I would like to continue with this side the oil and this side the water. So you can use on the same page just two columns. So in terms of the overall heat transfer coefficient, if we just look back here, then we can see that we need the heat transfer coefficients on the inside and the outside. And we need the areas on the inside and the outside. They've given us not any information on the wall except to say it is a thin wall. So we will get to that a little bit later. But I think the focus at this stage, as you can see, should be quite clear, getting to two heat transfer coefficients. That is normally the big challenge when you work with heat exchangers. You need to get those two values. Now let's start with the water side. Of course, the water is just a circular tube, and we can start by saying that the mass flow rate is given as equal to rho OV, rho AV. The mass flow rate of the water was given as 0.5. The density of the water is 990.1. The cross-sectional area through which the water flows is pi divided by 4 multiplied by 0.020 square multiplied by the velocity. From here, we can calculate the velocity. as 1.61 meters per second. The Reynolds number is equal to, you can write it as rho Vd divided by the viscosity, or Vd divided by the kinematic viscosity. We've got the velocity is 1.61, the diameter is 20 moles, divided by the viscosity 0.602, multiplied by 10 to the minus 6. So the Reynolds number is 53,490. It's larger than Reynolds numbers of approximately 2,100 to 10,000, so it's definitely turbulent flow. The flow is turbulent, it's a circular tube. There are several equations in your textbook that you can use. The Sider-Tate equation, the Dieters-Boulter equation, Glinsky equation, etc., etc. I'm lazy, so I'm going to say, well, the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter multiplied by the diameter divided by the thermal conductivity is equal to 0.023 multiplied by the Reynolds number to the power of 0.8. Prandtl number can either be 0.3 or 0.4. Okay. 0.4 is if the fluid is being heated. Okay, you've got water, it is being heated by the oil. So therefore the Prandtl number should be 0.4. There's the Reynolds number. Okay. The Prandtl number of the oil, the water is 3.91. So it is very elementary to go and calculate the heat transfer coefficient as 7,663 watts per square meter degrees Celsius. Let's look at the oil side. Now the oil flows through the annulus, so through there. So we can make use of the principle of the hydraulic diameter. For an annulus, it is equal to the change in diameter, and that would be 30 millimeters minus 20 millimeters. It is then 10 millimeters in terms of the hydraulic diameter in meters. The mass flow rate is then equal to rho AV. Okay. The mass flow rate of the oil is 0.8. The density of the oil is 852. Cross-sectional area, pi divided by 4, multiplied by the cross-sectional area through which the flow flows. Multiplied by these. So we can calculate the velocity of the oil is actually higher than that of the water. The water velocity is 1.6 meters per second. This is 2.39 meters per second. So the velocity is higher. If you now look at that and you say, well, now this flow is also going to be turbulent, you're going to make a big mistake because the viscosity really plays a big role. So the Reynolds number is equal to the velocity, the diameter, divided by the kinematic viscosity. Now we're going to use the Reynolds number based on the hydraulic diameter, and that is equal to 2.39 multiplied by 0.010 divided by the kinematic viscosity 3.794 multiplied by 10 to the minus 5. So the Reynolds number is only 630. So this flow is laminar flow. It's not turbulent. Right, now for flow through an annulus and for laminar flow, in your textbook there's a table of data which are being given by Keyes and Parkins of 1972 in your textbook, and based on the diameter ratio of the annulus, which is equal to 0.020 divided by 0.030, which is equal to 0.667. I'm running out of space, so I'm still busy here on the left-hand side with the oil. Remember, that side is the water. If you can't read this, the diameter of the inside divided by the diameter of the outside. The inside is 0.020, the outside is equal to 0.030, and that ratio is equal to 0.667. So for that ratio in that table, you can go and get the Nusselt number is equal to 5.45. And this Nusselt number is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by K. The Nusselt number is equal to 5.45. Is equal to the heat transfer coefficient multiplied by 0.1 divided by the thermal conductivity is equal to 0.138, and that will give a heat transfer coefficient of 75.2 watts per square meter degree Celsius. Okay, now you can break the two columns. We have to put everything together now. We've calculated the heat transfer coefficient on the inside. Let's call that HI on the inside, and the heat transfer coefficient on the outside. So, in terms of this equation of 1 divided by the overall heat transfer coefficient multiplied by the surface is equal to 1 divided by the overall heat transfer coefficient on the inside is equal to the area on the inside is equal to 1 divided by the overall heat transfer coefficient on the outside multiplied by the area on the outside is equal to the total resistance is equal to 1 divided by the heat transfer coefficient on the inside plus the area on the inside plus the fouling on the inside divided by the area on the outside plus, in this case, the resistance of the wall is the diameter ratio divided by 2 pi KL plus the fouling on the outside, the area on the outside plus 1 divided by the heat transfer coefficient on the outside and the area on the outside. Are you all with me? Okay. Right, so we have to get what they ask us to determine the overall heat transfer coefficient. If we look at those terms, we've got this value, and we've got that value. They didn't give any information on fouling, so we can neglect that. Okay. Now coming back to this sketch here, the ratio of the diameters. So it's the lin of 30 millimeters divided by 20 millimeters. You agree? No, you shouldn't agree. Okay. Because this is the resistance of the wall where the heat transfer is going to occur. So that is the wall where that separates the hot oil. In what direction did I? There it is, like that. So there's the oil, and here's the water. Okay. And the heat transfer occur, of course, over this wall. So the heat transfer is over that wall. So the resistance, RW of the wall, is that diameter divided by this diameter. You see? Which they didn't give. They actually said it's thin. Okay. So if it is thin, means that this term is obviously incorrect. Thin would mean that on the outside maybe it is 20 millimeters, and on the inside it is 19 millimeters, the lin of something like that. And that would be approximately 1. You agree? If the diameter, if it's a very thin wall. And the lin of 1 is equal to 0. So the moment we've got a thin wall, that resistance is also negligible. Okay? Right, so if we now look at this equation, this is the area, the inside area, and that is the outside area. If the wall is thin, then those two areas are approximately the same. So therefore, in terms of this area and that area, those areas are all the same. Okay. So the surface area is equal to the inside area is equal to the outside area because it's a thin wall. Okay. Therefore, this equation, which is quite not nice to go and calculate if you've got all those terms to substitute, now reduces to 1 divided by the overall heat transfer coefficient is equal to 1 divided by the heat transfer coefficient on the inside plus 1 divided by the heat transfer coefficient on the outside. Yep. Up to when is it a thin wall? It is a judgment call of you as an engineer. Obviously, in the tests and exams and the chapters in the textbook, I would say a thin wall, then you know. Okay. But you as an engineer, if you have something in industry and you're not sure, just go and calculate those two values and check how close it is to 1, and just check and just go and calculate the lin of it, and you'll then see if it is very small or not. Now remember, it is not only this term on the top which is important, that lin ratio. The other thing that normally works into your favor is the thermal conductivity. Because if it's copper or stainless steel, that value is large. And also, if you now divide by a large number, it makes the term even smaller. So those two things are actually important, that combination. Right, so if we now look at that, we can say 1 divided by the overall heat transfer coefficient is equal to 1 divided by the heat transfer coefficient on the inside, 7663, plus 1 divided by the heat transfer coefficient on the outside, which is equal to 75.2. Okay, so the overall heat transfer coefficient is 420 watts per square meter degree Celsius. You happy with that? Do you agree? It is incorrect. Incorrect. I want to go back to what I said yesterday, that when you calculate these values, you have to be critical when you look at all the values, because they tell you as an engineer where to go to and or where your challenges are. If you look at these two heat transfer coefficients, you'll see this one is almost 8,000 and that one is small. This small one is always your challenge. So it's not that I'm good with mathematics or anything like that, but if I look at this, I should immediately know the overall heat transfer coefficient is going to be dominated by that value. So this value and that value should be about the same. So this can easily happen if you make an error on your calculator. So if you go and recalculate it, it is actually 74.5 watts per square meter degree Celsius. So what you now can see is that this value and that value is approximately the same. You see that? So you can calculate as many resistance terms as you want. In many, many cases, there's one of them which are the dominant one. And you as an engineer, if you want to improve your heat exchanger, want to make it more effective, that is where you should spend your money on. So if you would now look at this specific case where we've got the water on the inside and the oil on that side, if you would go and put in some fins here on the water side to try to improve the heat transfer coefficient on the inside, you're just going to waste your money. And you're going to cause a bigger pressure drop, and your pump will have to work harder to get the fluid flow, to get the fluid through. You should concentrate on the oil side in this case. Why? Because the heat transfer coefficient is an order of magnitude smaller. So if you would now go onto the oil side and you would put in some fins or enhance the heat transfer, then the heat transfer coefficient is going to improve significantly. And therefore you're going to end up with a more effective heat exchanger. Any questions? Do you understand that? So what I want to ask you is, when you design heat exchangers or do some calculations, do not just go through all the motions and trying to pump everything into this equation so that you can use it later on to say heat transfer, the overall heat transfer rate is equal to UA multiplied by LMTD. Don't do that. Think about all these values and what they really mean. Any questions? Okay. Another example, I'm not really sure we're going to finish it, but let's see what we can do. Again, a tube-in-tube heat exchanger. We are starting very easy with the tube-in-tube type of configurations, the double pipe heat exchangers, just because it's the simplest type of geometry at this stage. And in this case, we are going to have the hot fluid flowing through the inside and the cold fluid flowing through the annulus. Like that. And now, these diameters are given there. And they are given as 15 millimeters on the inner diameter, and that diameter as 19 millimeters. So I'm going to draw it a little bit bigger so that we can make it clearer. So that diameter is, and we typically use the notation, the first digit indicates it's on the inside, and the second one, which part of the inside tube. So that diameter is equal to 15 millimeters. And then that diameter, again of the inside tube, but on the outside is equal to 19 millimeters. So there's the tube wall like that. While if this is now the annulus, we would typically indicate that diameter as the outside diameter of the inside, and from there to there, the outside, the outer tube, the outer diameter on the outside of it. So there you see the different types of notations that can be used. What is also given is that this heat transfer coefficient on the inside is equal to 800 watts per square meter degree Celsius, and the one in the annulus, the heat transfer coefficient in the annulus, is equal to 1,200 watts per square meter degree Celsius. And then they're going to give us some information on fouling. And the fouling, remember, fouling is not normally going to happen on the annulus, it's going to happen on this surfaces there, where you've got the heat transfer. So it is that surface there, so there's that surface there, and there's going to be fouling there. And then again there and there. Okay. Now the fouling on the inside is given as 0.0004 square meters per Kelvin watt, and then the fouling on the outside is equal to 0.0001 square meters per Kelvin watt. Square meters Kelvin per watt. Okay, so the resistance of the fouling on the inside, the resistance of the fouling on the outside. Okay, now I see I'm going to run out of time. So if we look at this resistance term, which we can write as 1 divided by the heat transfer coefficient on the inside, the area on the inside, plus the fouling on the inside, the area on the inside, plus the ln of the diameter ratio divided by 2 pi KL, plus the resistance of the outside divided by the area of the outside, plus 1 divided by the heat transfer coefficient on the outside and the area on the outside. You can go and calculate the area on the inside as equal to pi dl, and it is equal to pi multiplied by 0.015, and we are going to use it to do it per meter. So the length is going to be 1 meters. So this area is equal to 0.0471 square meters per unit length. Going to do it then on the outside. In this case it is 19 millimeters. And this is going to be 0.0597. There's not going to be time for me to do all the substitutions. They're also going to give that this is a stainless steel heater, heat exchanger, So the thermal conductivity of the stainless steel is equal to 15.1 watts per meter Kelvin. So what I'm going to do is I'm going to skip putting it, do all the substitution. I'm just going to give the values. So it is going to be 0.02654 plus 0.00849 plus 0.0025 plus 0.00168 plus 0.01396. Just to make sure that we understand. So this thermal resistance is going to be that value there. Okay. So in this case, the diameter on the outside is 19, and now it is 15. The limb is still going to be close to 1, but it is not going to be 1, so it's something, and then you're going to divide by the thermal conductivity, which is, in this case, 15.1. You're going to calculate that, and according to the total value, which is going to be 0.0532 degrees C per watt, you could see in this case there's not one specific term which is extremely dominant. Okay. So this problem has now been carefully selected. But what it shows is that this part of the problem would be 5% of the resistance, while the fouling part would in total contribute 19%. And the two convective terms, those two would represent 76% of the total resistance. So therefore, if you are looking at these values critically and you want to try to improve the performance of the heat exchanger, changing it to a thinner wall, increasing the thermal conductivity, is not going to significantly change the total resistance. The fouling is there. In total, it's going to end up as about almost 20%, but most of the resistance is into the two convective terms. So in this case, if you want to improve the performance of the heat exchanger, you can look at increasing the velocities, maybe through the inside and or the outside, or by changing the surface area. Is that clear to you? Right. Thank you, ladies and gentlemen. Then I'll see you again next week.